Hello, everybody. Welcome to this little presentation about the Polygon Mesh library. My name is Mario. I'm from Bielefeld University. I'm about to move to Dortmund University, which is also written here. So the Polygon Mesh Processing Library, or PMP library for short, is developed by Daniel and myself. Daniel is working for Covento, but he's working on PMP basically in his free time, so I put him here as private investigator. So let me tell you a bit about the Polygon Mesh Processing Library. It's a C++ cross-platform library. It runs on Linux, Windows, and Mac OS. And it provides a simple and efficient half-edge data structure. It has a set of geometry processing algorithms and ready-to-use simple visualization tools. So we think it's useful for several use cases. So if you are in research and development, it's nice because it's one simple package without external dependencies. So it's easy to get started with PMP. It also allows you to cross-compile your code to WebAssembly applications. So it's easy to produce online demo applications that you can put on your website to show off your latest research. Maybe if you don't want to distribute your source code, you can at least show an application. But in any case, you should distribute your source code. These little web demos are also very cool for teaching. So I use it a lot because students can then try out the algorithms that we teach, try the different parameters and see how the algorithm reacts. But maybe you're not from academia, but from industry, you can also use PMP to develop industry applications. And you might be happy that the data structure and the algorithms have been tested for about 10 years now. The source code has industry strength quality because whenever I do a commit, Daniel makes sure that it's modified to meet his high software engineering standards. And also the library allows you to use the PMP library even if you develop commercial applications. So these three parts that PMP provides is also the structure of this little presentation. Let us first talk about the data structure itself. So about 10 years ago, we asked ourselves, what makes a simple and efficient Polygon mesh data structure? And this is basically a compromise in both design and implementation between computational efficiency or memory consumption or a wide applicability and finally ease of use. So from these four, we put ease of use as our main focus because we want to use the data structure also with students or with beginning developers. So we want to have data structure where you can easily get started. So this is also reflected in the different design decisions that we have. So first of all, you have to decide for a mesh data structure whether you want to support triangles or arbitrary polygons. And we wanted to be as flexible as possible, so we decided to support arbitrary polygons. Then the question is how to store the connectivity. Do you store it in a face-based data structure or an edge-based or half-edge-based data structure? And because with a half-edge-based data structure, you have all the different entities like vertices, edges, half-edges, and faces. And all these entities have a constant size. So we decided for a half-edge data structure. Then all the elements can be stored in either linked lists or arrays. And while lists may be more flexible, arrays are more efficient both in terms of memory consumption as well as in terms of like computational performance. The different entities then need handles or references, and if you use arrays, then it's quite natural to use indices into these arrays as references for the elements. And on a 64-bit architecture, it's also quite nice that a 32-bit integer is about half the size, or it's exactly half the size of a 64-bit pointer. So also memory-wise, this makes sense. Then all the different entities might have to store special properties like a scalar per vertex or a point per face. And these custom properties can be implemented in a clean object-oriented manner by extending the entities. So you have an array of structures, or the structure of arrays, you have like several arrays, so every new entity, every new property you store in an additional array, and all these arrays are synchronized. And we decided for the latter because it's easy to dynamically allocate and deallocate these properties. Finally, the important point, ease of use. So how do you want to organize this data structure in terms of API? So should we use a very minimalistic MATLAB-like API like libigl does, or something super fancy and sophisticated with lots of templates like Seagull? And we decided to do something in between. So it is C++, we have classes, but also for efficiency reasons, it's not a full fancy object-oriented design, but a rather simplistic C++ design. So when we implemented this in 2011, the main data structure, we started from OpenMesh, like OpenMesh. The first paper goes back to 2002. When I was a PhD student in Aachen, we worked on that with a couple of other people, and many people have contributed to OpenMesh since then. So we use it, but one of our design goals is ease of use. So we massively simplify OpenMesh because, like, whenever I used OpenMesh for teaching, students, maybe it's a problem of our students, but they always complain that it's too complicated and they wanted to have a simpler data structure. So we removed about 75% of the code in the core data structure without losing functionality. So we just stripped it down to the bare minimum. It's a single class instead of a complicated inheritance hierarchy. We avoid using templates. There are some situations where you need templates, but we reduced it to a minimum. And we use modern C++ constructs to make it easier to use, like range-based for loops, as I will show you on the next slide, where we have a little code example. So what we see here is a full application that reads a mesh, does some smoothing, and writes it again. So let me walk you through it. We include the surface mesh header, use its namespace, the PMP namespace for Polygon mesh processing library. And then we define and read a mesh from a given file name. Now, for the sake of this little example, let's say we want to do uniform Laplacian smoothing. So for every vertex, compute a new position as the average of its neighbors. So we add a point, like a 3D point, as a custom property to the vertices, stored in this variable here. And then we perform 10 smoothing iterations, where in the first step, we iterate linearly over all the mesh vertices. For every vertex, we compute a new position as the barycenter of its neighbors. The barycenter is initialized to 0. We iterate through all the neighbors of this vertex, all the vertex neighbors, add their position to the barycenter, and in the end divide by the valence of the vertex. This gives us a new position, which we store in this custom vertex property, which is just a synchronized array, as also indicated here by this syntax. Once we have computed a new position for every vertex, we just go through the list of vertices again and update the vertex position to be the new position. We do this 10 times, and then we write the mesh to a file name that is given on the command line. But this is just a quick example to get a feeling on how complicated or easy the data structure is. So when we designed it back in 2011, we did some quite comprehensive benchmarks. So the numbers are listed here. They are totally outdated right now, but just that you get a rough feeling. So we compared at this time to the polyhedron implementation of Seagull, both the list version where everything is stored in linked lists or in vectors, and we compared to OpenMesh and like PMP, and it's all relative to PMP, which is normalized to 1. And like based on the numbers from 2011, we use fewer memory and fewer computation time than the other data structures. So we were quite happy. And in the end, this is also quite cool, Surface Mesh was then integrated as an alternative mesh data structure to the polyhedron into Seagull. So if you like the PMP and Surface Mesh, but you want to have more templates, then have a look at this. And then you can also apply all the cool Seagull algorithms to this data structure. So we also provide a couple of algorithms, but it's like by design, not the like a dump for all the latest research code. The algorithms that we provide are, as written here, more canonical, the standard algorithms that you expect from such a data structure. They have been tested over time. It's not the latest research code. So let me show you a couple of examples. So we have most of the algorithms for the like classical mesh processing pipeline. Let's say you scan an object, a person, then you generate a mesh, and then you start mesh processing. So you can, I don't know, compute all kinds of curvatures. So you see the mesh is noisy, either because you scanned an old person with lots of wrinkles or because of scanner noise. Where we see the mesh structure here. So the first step might be remove the noise by some diffusion flow smoothing. And then if the mesh is too complex, like shown here, we have standard iterative quadric error metric decimation. So let's, I don't know, decimate it to 25%. Shown here. But then maybe you don't like these long triangles anymore. You want to have nicer triangles. Maybe you also want to have like adaptive triangulation. So we also have uniform and adaptive remeshing here, where you can put more parameters if you want to have a denser mesh, or you just do subdivision. Or if you don't like the hole that we have here, we also have an implementation of Lipa's hole filling technique. So all these standard algorithms do exist in PMP. If you work on like CAD-like data, feature preservation is important. So in most of the algorithms that we have, that we put in the correct value here, if you have these sharp features, they are also preserved if you do mesh processing. So we support not just triangles, but also general polygons, which is shown here for a mesh with mostly quads, but you see it's also some triangles. It's this like Blender mascot model. And like Catmull-Clark, for instance, produces all quad meshes, as we see here. And then depending on the squeeze angle, you can adjust the rendering. So this is also supported. In terms of parameterization, we have the classical discrete harmonic parameterization or least squares conformal maps, where like the latter we implemented in a way to support open boundaries. So if you want to have a Bavarian style Beetle model, here you go. We also use this for research, and here is a demo of our recent Eurographics paper where we generalized the cotan Laplacian to arbitrary polygons. So this is not in the PMP library. It was built using PMP library, and parts of it might probably be integrated into the library. But just to give you some more demos, so we have geodesics in heat, where you need Laplacian and gradient and divergence operators, or but if you have a general Laplacian, you can use it for smoothing. So let's do like super aggressive smoothing on this quad mesh. So this is like the conformalized mean curvature flow of Misha. So this poor guy converges to a sphere, while all the holes that the mesh has are just considered to be like one big general polygon. So no special handling is required here. So much for the algorithms that we have. What about the visualization and user interface that you see all the time? So this is by design quite simplistic. So the window management and like user interaction is like GLFW, which is very minimalistic. Rendering is done by OpenGL, like the core profile 3.something OpenGL, or WebGL if you cross-compile it to a web demo. The user interface is ImGUI, which we customized a bit to look nicer. This was recommended to us by Bruno Levy, so thanks a lot for that. It's an immediate mode user interface that is just based on OpenGL. So this is like very easy to incorporate. And then for these web demos, we cross-compile our C++ code using mscripten to WebAssembly. So basically all the applications you build with PMP can be cross-compiled to run in your browser, either on your web page or if you use cool HTML slides, then also in talks and presentations and in teaching. And so this is rather minimalistic, so you don't build very fancy user interfaces with that, but we found it's like great for prototyping and great for teaching. Now I've shown you what the PMP library provides, like this very simple, nice data structure, a set of algorithms, and also simple and nice and easy to use visualization tools. Now, when should you be willing to use it? So how to differentiate PMP from the other libraries that exist? So for instance, when should you use PMP instead of libIGL? And so in our opinion, like libIGL supports triangles only. So if you want to work on general polygons and I want to develop something where you need dynamic connectivity, like remeshing or decimation or something like this, then PMP is probably the better choice. What about Seagull? When to use PMP instead of Seagull? This pretty much depends on how sophisticated or professional, profound you are in C++. If you want to have something small and simple without templates, PMP is probably the better choice. If you are a professional software developer and you're not afraid of modern C++ and templates and you want to use all the cool algorithms Seagull provides, then go for Seagull. Open Mesh and Open Flipper. So like Surface Mesh is based on Open Mesh, and then PMP adds the algorithms to it, like Open Mesh adds lots of algorithms. Open Flipper adds lots of algorithms to Open Mesh. So here, like both Open Mesh and Open Flipper are quite larger, less simple, more sophisticated maybe. Also has some more templates. So if you want to have something small and simple without templates, then go for PMP. Then we also have VCG and MeshLab. And this is not small and simple, and it doesn't support general polygon meshes. So the main point probably is general polygon meshes and dynamic connectivity, and something that by design is small and simple. And from what I've read, but I don't know yet, this seems to be like very well aligned to the design goals of the geometry central data structure, which we don't know yet. So we are curious about their presentation. Now, if you want to give PMP a try, pmplibrary.org is the website, which you also see here. The code is hosted on GitHub, so feel free to check it out. You even find like one of the online demos on this website. Just go to the user guide and to the quick start, clone it, build it, compile it, and play with it. We have a small tutorial that gets you started, and just try it and let us know whether you like it or not. So if you try it, and please give us feedback. So if you like it, please send me an email. If you don't like it, please send Daniel an email, or file an issue on GitHub. Feel free to contribute. It's an open project, so currently it's more or less just Daniel and myself, but feel free to contribute to it. If you use it, please let us know that you use it, and let us know what you use it for. That would be very interesting for us. Right now, we have no idea who is using it and for what kind of application. And if you use it, then please acknowledge it. So that was my small presentation about the PMP library. I hope you liked it, and I'm looking very much forward to our Q&A session at the Grad School of SGP. So see you there.